Hey, geometry friends, here we are. We're looking at chapter 7 and we're looking at ratios and proportions. We've got a couple of vocabulary words. You're familiar with a ratio, right? And a ratio is basically a rate. And so I could say, I like to use this one, if I go up to make, a bunch of free throw shots, like 10 of them, I probably make 1 out of 10. That's a ratio. So for every one I make, I've already tried to shoot 10. So look at this. These are different ways of writing ratios. Ratio is just a way to compare two numbers, right? So that's a ratio, a comparison. Then we have extended ratios. So I could talk about, when I was 16 and I wanted to be class president, right, of my sophomore class. And so I and 3 of us, we were, running against each other. And I got 2 votes for every 3 votes one of my challengers got, and for every 5 votes that the winner got. So me, some challenger, and the winner, right? So if this was, obviously you can see that the ratio of our votes, this is an extended ratio because it's between more than just 2 things. It's a comparison, in this case, between 3 numbers. Does that kind of make sense? We'll talk about how to solve problems like that. All right, so now we've got the idea of a proportion. A proportion is when you have 2 ratios that are equal to one another. So I might say, remember me making 1 out of every 10 shots when I go up for a free throw? And so I might say, all right, then, so if I go up for 53 shows of free throws, I can say words. If I go up for 53 free throws, I'm trying to say it, then how many would I make according to this ratio? And this is a proportion. A proportion literally is when you set 2 ratios equal to one another, and it gives us the power to solve this. Hopefully you guys are looking at this and you're like, clearly you would only make 5, which would be correct. So the idea of extremes and means, and we're going to come to a nice visual of that in a moment. So remember when I mentioned that a ratio can be written in 2 ways. So if I wrote a ratio as a fraction or a ratio with this colon here, I could write a proportion. Remember, a proportion is when I said 2 ratios equal to each other like this. So watch this. 2 to 5 is the same as, let's say, 10 to 25. All right, 2 to 5 is the same as 10 to 25. And that's a true ratio. That's a true statement. When we look at this situation, the extremes are considered the numbers on the outside. So I'm going to highlight those in yellow. So extremes, I'm going to highlight in yellow, and I'll highlight the extremes. So if you think about extremes, they're the things that are furthest on the outside. And the means would be the stuff in the center. And so that's these guys on the inside. And then so there's this rule that we'll talk about that says the product of the means, 5 and 10, is equal to the product of the extremes. So the means are these numbers on the inside, and the extremes are the numbers on the outside. Stay with me for a minute. So watch this. If I have 2 over 5 is equal to 10 over 25, notice I'm writing the same exact proportion, but as fractions. If I've got that situation, look at this, if I multiply the extremes, I'm multiplying 2 times 25, like that, and the means, I get 5 times 10. And this is where you hear the product of the means is equal to the product of the extremes, or it's the cross products. And so that's where we get our last definition, the cross products. And this is something that we've done before in algebra. So with all that information behind us, let's take a look at this first example. We're going to write and simplify ratios. So here we go. A baseball player's batting average is the ratio of the number of base hits to the number of at-bats, not including walks. Minnesota Twins Joe Mauer had the highest batting average in Major League Baseball in 2006. If he had 521 official at-bats and 181 hits, find his batting average. All right, so lots of information there, and if you are not familiar with baseball, this probably sound like gobbledygook. So anytime you have a word problem like this, you want to try to, distill the essence of what they're asking. So I know they're talking about at bats and they're talking about base hits, and that's the thing that they're comparing. So I'm going to try to focus on that in the numerical part of this. So let's take a look. A baseball player's batting average is the ratio of the base hits to the at bats. So I'm going to write that down as kind of a little bit of a guide for me. So we're going to put base hits at the top and at bats at the bottom. And now I'm going to come to this information about Joe Mauer, and I'm going to check out that it says that he had 521 at bats and 181 hits. So that lets me know I'm going to put 181 on the top and 521 at the bottom. So what we're going to do here is we could honestly leave it like this. I don't think that this actually reduces very nicely. But what we're going to do is we're going to convert this to something called a unit ratio, where the denominator is 1, and that's going to give us his batting average. And so what we do is we basically plug it into a calculator, and so we'll get that the answer is approximately 0.347 to 1. And that would be Minnesota Twins Joe Mauer's highest batting average in 2006. So here's one of those extended ratio problems that I mentioned. So here in example 2, we're going to use extended ratios, and I want you to pay close attention to what we're going to talk about. So we've got the ratio of the measures of the angles in a triangle is 3 to 4 to 5. Find the measure of each angle. So what this means is like there exists some x value, right? Such that 3 times x is going to be one angle. And that same x value, when I take that and multiply it by 4, that'll be some other angle. And that same x value, I'll multiply that by 5, and that'll be the other angle. If you think back to my example when I told you about the fake election that I had, and I got 2 parts of the vote and somebody got 3 and somebody else got 5, I really never actually went out for public office because I was too super cool. So however, in this case, this is from, I'm going to put it in a thought bubble. In this case that we were talking about before, when we were dealing with our vocabulary, we would have done the same thing. I got 2 parts of the vote, whereas somebody else got 3 parts, and the winner got 5 parts of the vote. So we're going to do something like this. Let's say we knew that my class had 1,000 kids. Then you would break it down like this. You would say 2 parts plus 3 parts plus 5 parts of some amount. All of that has to add up to 1,000. That's that example. Let's get back to this triangle. So we know that the sum, this is kind of unattractive. Let me make this prettier. I think this will do it. So now I'm going to move this over here, and let's say this is my 5x angle and this will be my 3x angle. I'll make this a nice small one over here, and this angle over here is my 4x angle. So 4 times some number plus 5 times some number times 3 times plus 3 times that number has to be 180, right? Because we know that the sum of the interior angles of a triangle would be 180. So I get this equation here. And so they want us to find the measure of each angle. Well, the first I need to find this x value, then I can tell you the measure of each angle. So let's go ahead and do it. I'm going to add up 3x plus 5x plus 4x is going to give me 12x. Then I'm going to solve for x by dividing both sides by 12. And so I get that x is equal to, let me do some quick math here. I'm going to have to reduce, guys. Divide top and bottom by 6, and I get 30 at the top and 2 at the bottom. And so x equals 15. Let me know if that's wrong, because sometimes I make mistakes. All right, so if x is equal to 15, then 3 times x is going to be 45. So this is a 45-degree angle. If 4 times x, if x is equal to 15, when I'm talking about 4 times x, that's going to be 60 right there. And then 5 times x, that's going to be 75. Does that make sense? So that I've finished off the problem by coming up with the answer to the question, which is to actually find the measures, not just find the x or the thing that we were comparing in terms of their ratios. All right, let's take a look at another one. So this is kind of a graphic, a better graphic actually, a better illustration of what I was talking about earlier in terms of the extremes and the means. And you see that these the extremes are generally on the outside and the means are on the inside. And when you write them as fractions, it would be like 2 over 3 is equal to 6 over 9. And then you get the extremes here and then the means here, like we see over here. And that gives us the power to use the cross products, right? In a proportion, the product of the extremes equals the product of the means. So this is right in your textbook. Feel free to photograph this, take a look at it, memorize it, all of it's good. So here in example 3, we're going to use cross products to solve. And this is something, as I mentioned before, you probably did in algebra. So basically, if I've got two proportions, or if I have two ratios that are equal, meaning a proportion, I can cross multiply and the products should equal. Since the product should equal, it'll give me an opportunity to solve for a variable. So then over here I've got 6 times 31.5. So we get 21x is equal to 1,890. And you guys know how to do this. We're just going to divide both sides by 21. And what we'll get is, we'll get 90 when we finally divide everything out and simplify. So the next one over here is the same thing, but it looks a little bit more intimidating because you got this x plus 3 here, but it's going to work out exactly the same way. We're just going to rock a little distributive property in the house. So 5 times the quantity of x plus 3 is equal to 2 times 4x. And so what we'll do is we'll get 5x plus 15, rock that, right? Don't forget, is yes, 5x plus 15 is equal to 8x. And we're going to do what we do. We're going to subtract 5x from both sides. We'll get that 15 is equal to 3x. Divide both sides by 3, and you see it, x is equal to 5. So if that's the case, x is equal to 5, we need to finish this off. I started writing some nonsense here. Let me clean that up. 5 plus 3 is 8. So we get 8 over 2 here. And 4 times 5, or 5 times 4 is 20. And we have 20 over 5. And you can see 8 over 2 is equal to 20 over 5. So we have solved the proportion. All right, we have one more example here. Fernando conducted a survey of 50 students driving to school and found that 28 owned cars. If 755 students drive to school, predict the total number of students who own cars. So this kind of gets into a little bit of statistics. So when we deal with statistics, like when people say this many people support whatever, and you say, well, how do they know because they didn't ask me? There's a statistical fact or a statistical belief that if you have a decent enough random sample size of people, you can kind of predict what the rest of the people say. So if you get, let's say, 1,000 people to take a survey or a poll and you randomly selected them, that's a good indication of what the United States thinks. Isn't that kind of crazy? Only 1,000 people to indicate, but it has to be randomly selected. Anyway, with that in mind, that's what Fernando is doing. He conducted a survey where he only spoke to 50 people, and of the 50 people, 28 own cars. So I'm going to write this as 28 out of 50 owned cars. Good. So if 755 students drive to school, predict the total number of students who own cars. Well, what we're going to do is we realize that the whole group of students that he surveyed, out of them, this is the number that owned cars, that were car owners, right? This is the number that own cars. So this is the whole number of kids that he surveyed, and this is the number that own cars. Then we're going to assume that that whole number represent the whole population of 755. And then we'll throw an X up there and we'll solve. Does that make sense in a way? So we want to know how many own cars out of 755. That's my whole. And we know that Fernando's, complete total number was 50. So we're going to cross multiply, do the thing we need to do, and we get. So then I divide both sides and I get that X is equal to, with the help of my calculator, I'll be honest, 422.8. So I would assume that about 423 students own their own car. I hope that made sense. I hope you saw some uses for proportions. Let me know if I can help you, and we can talk a little bit later, and I look forward to seeing you soon.